Hello, welcome to a very short or one-off video on acids and bases. Basically this will teach you or give you everything that you need to know about acids and bases. Even though we've done some work on acids and bases, it just gives you a bit of context to what they are and how they work. Now, some common acids and their uses. Now, most of these we've come across before, and remember that the formulas for these aren't given to you on your information sheet. Sometimes they'll be given to you in questions, but mostly you'll have to try and remember the common ones: nitric acid, hydrochloric acid, sulfuric acid, acetic acid, and then we get a bit these ones down here you don't really need to know about, but they're there because they're common. Citric acid, found in lemon juice. Carbonic acid, found in soft drinks. Lactic acid, it's what makes milk sour. It's also in some face creams. And ascorbic acid, which is also found in citrus fruits. So there's some common acids, some of which you've heard about and some of which you haven't, but the acids are around us and we use them all the time, not just in chemistry experiments. Bases are probably something that you haven't heard as much about, but they're also very, very common. And these are some common bases. Ammonia, NH3, it's in fertilizers and detergents. Often when you're cleaning things, one of the smells that you smell is ammonia, particularly if you're using a strong cleaner. Sodium hydroxide or caustic soda, it's in soaps and detergents. Sodium carbonate, it's used in glass manufacture. Calcium carbonate, it's in brickies mortar. Lead oxide was in house paint, but now it's phased out because lead isn't good for you. Calcium hydroxide, ammonium hydroxide, and magnesium hydroxide. So notice that they're hydroxides or metal oxides basically, apart from ammonia. Now, what are some of the properties of acids? Okay, they taste sour. I wouldn't recommend that you taste any of the acids we use in the chemistry lab, but when you eat an orange or have some juice, fruit juice, that's the acid is giving the sour taste. They're corrosive, are molecular, so they're covalent molecular, and will dissolve in water to produce an electrolyte. That means that there must be a positive and a negative ion when they dissolve in water. Even though they're molecular, the molecule can be broken down by water. They affect the colour of certain natural and synthetic dyes. Litmus, you may have heard of litmus paper, and so they change litmus paper from blue to red, and they are neutralized by bases. Remember when we did reactions, we looked at an acid-base reaction, and you get a product of a salt plus water, so they're neutralized. Properties of bases, which are probably less common, but you have experienced them. They also taste bitter. They feel slippery, so if we've been doing any experiments with bases and you've got a little bit of base on your hand and then you wash them, it actually feels smooth and slippery because they're corrosive. They're just taking a little layer of skin off, basically, and that's what gives you the smooth feeling. Wouldn't recommend you testing that. They also make litmus paper change colour, this time from red to blue. They're electrolytes, so they conduct electricity. Can be corrosive, so a lot of them are used as drain cleaners or oven cleaners because they're very good at getting rid of organic substances. Generally ionic substances, mostly oxides or hydroxides of metals, and are usually insoluble in water. But there are some bases that are soluble in water, and they're called alkalis. So some definitions. This is where it gets a little bit confusing, and you don't need to memorize this. You just need to understand what we mean when we say this. And so an acid is a substance that donates a proton. Now a proton is just a hydrogen ion, isn't it? Remembering that a hydrogen just has one proton and one electron orbiting around it, and if it loses that electron it becomes an ion, so it's a proton. So it donates a proton to another substance. In other words, it produces hydrogen ions, whereas a base is a substance that accepts a proton from another substance. So it will accept the hydrogen ions. And we'll see a couple of examples of what we mean by that. So a common acid that we use is HCl, and when it's in solution, you don't have molecules of hydrogen chloride, you have hydrogen ions and chlorine ions. And it's these hydrogen ions that make it the acid. Another acid is nitric acid, and when we dissolve it in water, the hydrogen from the acid actually goes onto the water molecule. Now this is not written up here because we really don't need to confuse physical science students with this, but we're introducing it to you now just so you know what the mechanism is, and it will help you if you go on to do chemistry. And so if this hydrogen ion goes and attaches itself to water, you get a H3O ion, which we haven't encountered before. And so basically the acid is acting as the acid, so it loses a proton, but water is acting as a base. And you haven't probably heard that water can act as a base, but it can. And it can act as a base because it accepts that hydrogen ion and becomes H3O+. And what we would call that is the hydronium ion. And it's a proton hydrogen ion. Because the hydrogen ion is so reactive, it doesn't exist by itself. So water molecules have, even though we consider them to be neutral, they actually have a distribution of charges, and the hydrogen ion actually latches on to the negative end of the water molecule. So it's not a very strong bond, but it's said to be forming the hydronium ion. Now this is the way we would write it normally in physical science, but if we factored in what was happening to the water, this is how we would draw hydrochloric acid, or write hydrochloric acid. In this case, hydrochloric acid is being bubbled through water, and you're getting a whole lot of hydronium ions and chlorine ions, or chloride ions. Now, so that's as much as you need to know in terms of acids and bases. Really, not much. Probably more to confuse you than anything. So, but you do need to understand what the pH scale is, and the pH scale is basically the hydrogen power. It's a measure of the concentration of these hydronium ions, and this is why we introduced the term to you in physical science, hydronium ions, because basically the pH scale is a measure of this, the hydronium ions in aqueous solution. So, but if you read a few textbooks, you may find that the hydronium ion is simplified just to be the hydrogen ion. So in reality you're getting this, but it's being simplified for this just to stop confusing people with what the hell this guy is. But we've introduced it to you to confuse you basically, but I hope it doesn't. So the pH scale, or the hydrogen power, is usually applied over a range of 1 to 14. And using this scale, a neutral solution is a pH of 7. Now you often hear people say that water, pure water, is neutral at 7, because it is. Basically, in water it has as many hydrogen ions and hydroxide ions and hydronium ions. They all cancel each other out, and it's neutral, so it doesn't have any hydrogen power, and it's not corrosive, it's not acidic, it's not basic, it's just got a pH of 7. Values that are less than 7 on the pH scale means it has, or it is, an acidic solution, so it has hydrogens dissolved and they want to react, because the hydronium ions, or the hydrogen ions, are very reactive. Now, the stronger the acid, the lower the pH value. For example, a solution of pH 3 is stronger than a solution of pH 4. That makes sense? Okay, and we'll show you a diagram. So here's neutral, here's our 1 to 14. Hopefully my face isn't in the way. This is increasingly acidic, this is increasingly basic. Some things that have. Now this top one is the acids, so 7's here, and as we go through to more acidic, we go through toothpaste, milk, carpet cleaner, dishwashing liquid. Tea is at about a pH of 5. Celery, orange juice, or is that, it's probably a grapefruit. Vinegar is down to 2.7 because vinegar is acetic acid. Then you've got the lemons, and then your other acids down at 1. Whereas for the bases, 7's here, and we're moving to 14 over here. We go cleaners, 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 stronger cleaners, ammonia solution, calcium hydroxide, very strong cleaner, and then dilute sodium hydroxide. Now, acids can be talked about in terms of their concentration or their strength, and again that confuses people as well. So you can have a strong or a weak acid. Now a strong acid, and if we just look at pure acid, now a strong acid has lots of hydrogen ions. If you look at this diagram here, there's lots and lots of hydrogen ions, and the HA represents the acid that hasn't dissociated and produced hydrogen ions. Whereas the weak acid, you've got a lot of the acid molecules and only a few of the hydrogen ions. Now these hydrogen ions would actually go off and make hydronium ions, but again we're simplifying it by just calling them hydrogen ions. So a concentrated acid has lots of hydrogen ions and very few molecules of the acid, whereas a weak acid has lots of molecules of the acid and not many hydrogen ions, and that's concentrated. So what about dilute though? Well, in dilute you just water it down, you've still got a couple of the molecules in the strong acid, and you've got a few of the hydrogen ions. But a dilute strong acid is still stronger than a dilute weak acid, because in the weak acid you've just got the molecules, you haven't got the hydrogen ions, or nearly as many of them. Here you've only got 3, here you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 or so. So it relates to the dissociation of the molecules and the production of hydrogen ions, the difference between strong and weak. Alright, and that's about all you need to know regarding acids. So, cheerio, and bases.